we'll be moving on to the last chapter in the course, chapter 13, where we take a look at Hamiltonian dynamics. And unfortunately, given time constraints, we can't look at Hamiltonian dynamics in very much detail. So it's mostly going to look like just an alternative to Lagrangian methods. But there are differences between the two. I mean, they are essentially equivalent, but there are advantages to the Hamiltonian formalism. And at our level, I'd say the most important thing is seeing some of the glimmers of a connection with quantum mechanics. We won't go into that in detail, but we'll see how there is some connection there between Hamiltonian classical mechanics and quantum mechanics. And it was that connection that led Dirac to some of his discoveries. He came up with the so-called Dirac quantization. Is basically you take a classical system, you write its Hamiltonian, and you follow a prescription to turn it into the quantum Hamiltonian for the quantum version of that system. So we'll take a look at how that plays out a little bit. But yeah, we're just going to learn the terminology, learn some of the characteristics of Hamiltonian dynamics. All right, so we've already met the Hamiltonian, actually. You remember that we had this result, which you've seen a few times, that if you have, say, the way I introduced it was, if you have an f which is dependent on x and x dot and t, then the rate of change of f is a combination of three factors. There's the contribution that comes from x changing, and then x changing with time. And then there's the contribution that comes from f's dependence on x dot, and then how x dot changes with time. And then there's the explicit time dependence, which gives us a partial f partial t. If f satisfies the Euler-Lagrange equations, then we know that we can rewrite one of the terms. Which one was it? Oh yeah, this one. We can rewrite partial f partial x as d by dt of partial f partial x dot. So plugging this in over here, what we get is df dt is equal to time derivative of partial f partial x dot times dx dt plus partial f partial x dot times d by dt of x dot, and then the remaining partial f partial theta. But then these two terms can be grouped together because this is in the product rule form, like f prime g plus g prime f. So here we have time derivative of this term and we leave dx over dt alone. Here we have partial f partial x dot is left alone, and we have another time derivative of x dot. So we can group those together to get d by dt of dx dt partial f partial x dot. All right, and then we can pull this to the other side. And so then finally, well, let me just rearrange things a little bit. So we end up with partial f partial t is equal to d by dt of dx dt partial f partial x dot minus f. And I'll just write that one more time, but write this as just x dot.
Where did that minus sign come from?
Oh, I moved the partial to the left side and the total derivative to the right side.
Okay, because in the line above that, it looks to me as if you have the partial and the total backwards.
No, so I moved this term here, so it lost the minus sign, and I moved this term here, so it gained the minus sign.
But I'm asking where the minus sign on that partial came from. Because in the line above it doesn't have a partial.
Oh, no, you are perfectly correct. You are perfectly correct. That should not be there. That should be a plus. This will be a minus over here. Yes. Thank you for catching that. All right, so we end up with this expression for partial f, partial t, right? Under those two assumptions we made that, well, no, one assumption that f satisfies the Euler-Lagrange equations. If we make now one more assumption, so if partial f, partial t is 0, right? If there is no explicit time dependence, then we have basically found a conserved quantity, right? We have x dot times partial f, partial x dot minus f is a constant. All right, so we've seen all this before, and now all we're doing is just changing the names of the terms a bit. So we've already said before that if you take the partial of the Lagrangian with respect to q dot, we call that generalized momentum. So what we have found for our conserved quantity is now basically, if I make the change from x to q, and then making this relabeling as well, what we have is q dot p minus L is going to be a nice conserved quantity, and that is called the Hamiltonian. So straight away, looking at our previous results, we see that, okay, if the Hamiltonian changes with time, it's only because of the explicit time dependence of the Hamiltonian. If there is no explicit time dependence of the Hamiltonian, then the Hamiltonian is conserved. And usually, not always, but usually, this conserved quantity will turn out to be the energy of the system. All right. So what can we further do with this? What is the equivalent of the Euler-Lagrange equations? Well, let's see. Let's just take the partial derivatives. So if I do partial h partial, let's say p, yeah. Well, no, let's start with actually partial h partial q. All right, so partial h partial q. So we have partial derivative of q dot p minus L. Okay, so q dot is independent of q, but p need not be. So, oh, hold on, sorry, my mistake. I should specify what we're holding constant. So this is actually, no, this is the partial derivative holding p constant. So p held constant. And okay, so what do we end up with then? Holding p constant times p minus, we have partial L partial q. But we have to be a little bit careful with this term because we are holding P constant, right? So what we do is we actually end up splitting it up. Sorry, 1 second. Yes. So let me write that again. So we have P partial Q dot partial Q holding P constant. We end up splitting this into partial L partial Q holding Q dot constant. Plus partial L partial Q dot holding Q constant times partial Q dot partial Q. All right, but partial L partial Q dot is just P. So this first term is going to cancel with this third term. Okay. And we end up with just minus partial L partial Q holding Q dot constant. This is partial H partial Q holding P constant. And this, from the Euler-Lagrange equations, we know is minus d by dt of partial L partial Q dot holding Q constant, which is minus, I mean, the term inside here is just the momentum, so this is just minus P dot. All right. So the only thing to be careful about is what you're holding constant. But what we see is a nice simple equation that the partial of the Hamiltonian with respect to Q will give us minus P dot. All right. And let's look at the other equation. Oh,
Sorry, could you just turn back briefly?
Sure.
I just needed to copy the last
Oh,
little
yeah,
bit
yeah, absolutely.
at the bottom. Okay, got it. Thank you.
Mm-hmm.
I also see the definition of P real quick at the top.
Yes. I realized that I'd forgotten to specify. So yeah, the definition of P was holding Q constant.
Okay.
All right. So that gave us partial H partial Q. What about, so let me just recap some of that here. What about partial H partial P holding Q constant? All right. So for that, we obviously get one contribution here. We'll get a Q dot term, but we know that Q dot is itself going to depend on P. So we also get a term for Q dot partial P holding Q constant. And then we have, from the Lagrangian, we get one more term there. The Lagrangian doesn't directly depend on P, but it does depend on Q dot. Q dot holding Q constant times that. All right. So we end up with these three terms. All right. But again, we recognize that partial L partial Q dot is just P. And so then now this third term cancels with the second term. And so we are left with partial H partial P holding Q constant is just q dot. And so Hamilton's equations are very nice and almost symmetric. What we have is that q dot is partial h partial p, and p dot is minus partial h partial q. All right, so a few things to note. So one thing that I should have specified more clearly at the beginning. So the Lagrangian is in general a function of q, q dot, and t. The Hamiltonian is a function of q, p, and t. And in fact, I think this is why we tend to denote momentum by the letter p. Is it came from these investigations into Hamiltonian mechanics. So he chose q for the coordinate. I forget why, but then p is another neighboring letter, and that ended up sticking for momentum. So we have they depend on they're functions of slightly different quantities. Hamilton's equations, you will notice, are first order differential equations. They only have a single time derivative. The price we pay is that we have twice as many of them. So there was only, like if you're looking at a 1D system, there was only a single Euler-Lagrange equation. Now we have two Hamilton's equations, but they're slightly easier because they're first order. But you can always rewrite the Euler-Lagrange equation as, again, essentially two first order equations. Yes, however, there are further details we'll get slightly into with regards to phase space that make this kind of reframing very helpful mathematically and computationally. Questions so far? Okay. Let's see. What do I want to cover next? Well, one minor point is ignorable coordinates. We've seen them before in Lagrangian dynamics. Basically, the idea is that if your Lagrangian doesn't depend on some particular coordinate. So for example, if we're looking in polar coordinates, typically the Lagrangian doesn't depend on phi. It does depend on phi dot, but not on phi itself. So that ended up having certain consequences. We end up seeing that angular momentum was conserved, for example. The Hamiltonian formalism tends to make that a bit more explicit, because if your Hamiltonian is not dependent on some particular coordinate qi, then the partial of h with respect to qi is 0, which immediately tells you that the corresponding pi is going to be constant. So we could do this again in the polar coordinates case for a central force and show that the angular momentum, which would correspond to the momentum conjugate to the phi coordinate, so the angular momentum will be constant. So yeah, so q and p occur in pairs, right? So even if you have multiple q's, each one will have a corresponding p. And what we say is that those q and p are conjugate variables. Notice that the product of Q and P, so we'd have meters and then times kilograms meters per second, which, let me see. Yes, right. Which it turns out we can actually rewrite in terms of joules and seconds. But there is something which has the units of joules seconds, and that is h, or h bar, Planck's constant. So we can start to see some of the connection here, and of course the pairing of x and p, or q and p, again is familiar from quantum mechanics. So we'll start to see a bit more of the connection as we go further in. Okay, just have 5 minutes. No, I guess that's a good stopping point. No need to shoehorn anything else in for the last 5 minutes. Just building off of what we've already done, just showing one nice result. I'm out of pages. Just need a few. I just need a little blank space. All right, whatever. If we look at dH dt, since h is dependent on q and p, we'd expect that, okay, well, this has 3 contributions: partial h partial q dq dt, plus partial h partial p dp dt, plus the explicit time dependence of h. But we know that partial h partial q is in fact minus p dot. So this becomes minus p dot. Well, actually, no, let me do it the other way around. We know that q dot here, right, dq dt is just q dot, and q dot can be written as partial h partial p. So the first term becomes partial h partial q times partial h partial p. And then we have partial h partial p, and dp dt is just p dot, but we know that that is minus partial h partial q. And we have the remaining partial derivative there. And so we see that these terms cancel out, and as expected, we are left with only the explicit time dependence. This sort of formalism where you have derivatives with respect to q and p is, we're going to see, leads to something called the Poisson bracket, which we will see in more detail later. All right, I'll stop there. Any questions? Okay. Hopefully you've seen the homework is pretty short this time. As I said on Moodle, spend the time working on your paper instead. Also, I've put links to some interesting gravity orbits simulations. So have fun playing around with those. Especially interesting are the many-body orbit simulations. There was some fantastic mathematical work that went into finding those. They're all unfortunately unstable, but they're called choreographies, where you have like maybe 3 masses moving in a figure of 8 just under Newtonian gravity. But yeah, have fun checking those out. And we'll continue with Hamiltonian dynamics and some problem solving on Wednesday. Right? Thank you.
Thank you.
Thank you.
Bye.
Have a good day.
You too.